Okay, let's get started without further ado. So welcome to lecture number 10. Yeah, progressing fast. And what have we learned so far? Just a very quick recapitulation of where we are. So in the last, I don't know, 5-6 lectures, the focus has been on pins, physics informed neural networks. And we have seen that for many PDEs, these are great, right? Especially if you don't have a lot of training data. This is something that I'm going to highlight quite a bit today. But as we saw in the last lecture, there are several negatives. In particular, the key negative that we found out was training can be expensive. Training is difficult. And the reason for that is this sort of intrinsic properties of physics-informed losses, where the Hermitian squared, the condition number of the Hermitian, the conditioning of the Hermitian squared of the differential operator really matters. So from that perspective, and also, if you remember that in terms of the PDEs themselves, what we saw is that they were very good for certain PDEs which had, let's say, smooth solutions, not too difficult solutions. But once you have difficult solutions, once there are lots of frequencies, lots of scales, which is the case in reality, then we are in trouble, right? So in that sense, we do need alternatives. And especially the alternatives make a lot of sense when more data is available. And how much of data is more data? We are going to talk about that quite a lot during the next several lectures. So now let's change perspective. And what we're going to do is, for the next several lectures, what we're going to do is to look at supervised learning. Supervised learning is essentially leveraging the data that is available to us, right? So we start now, and till the end of the month, at least, the month of April, that is, we will deal with this, perhaps even early in May. Okay, so let's get started. So before even sort of going towards data-driven solutions or PDEs, let me try to revisit or recapitulate the question of what does it mean to solve a PDE, right? So what does it mean to solve a PDE? What do we do when we solve a PDE? And this is going to be important for what we're going to discuss. So let's try to understand that through a very simple example, right? So this is a very important PDE. It's a prototype of what are called elliptic PDEs. So this is what is called elliptic. And this is modeling various things. So it depends on what your quantities of interest are. So for instance, the U here, this guy here, this could be the temperature, or it could be the pressure, or it could be some other property. But let's say that if it's the temperature or the pressure, then depending on the application that we have, the A here, so this is what is called a coefficient. For instance, if you're modeling heat conduction, then this A is precisely the conductance or the conductivity. It's the same if A or U is a voltage, for instance, then this is electrical conductivity. But on the other hand, if it's a pressure of a fluid that is trapped inside under the ground, then this would be the rock permeability, the sort of material properties of the medium itself. So this is the point is that it tells you something about the material, it tells you something about the domain where the action is happening. And finally, F, this is much simpler to understand. This is just a source term, right? So just imagine that you have a rod, which is made of a material that is not uniform, and then you start heating it. Then, of course, the source is the heating source. The material is given by the material properties, and U is going to be the temperature. And this is modeled by this elliptic PDE, which is called the diffusion PDE, or sometimes it's even called the Darcy PDE, particularly in fluid dynamics. So this is the situation with the PDE. So what we can think of is we can think of the PDE itself as a system. Like any system, it takes an input or inputs and it processes them into outputs. So what are the inputs? So at least for this particular PDE, this is clearly the coefficient. So this is A, and it is the source term, F. It could also be the boundary conditions, the domain, and so on. But let's keep things simple. Let's say that for this particular PDE, your inputs are the coefficients and the sources. And in particular, I could be interested in a situation, for instance, if I'm drilling under the ground, that I fix this. So let us keep this fixed. So if I fix the source, then essentially the task of the PDE, and I've forgotten to write what the outputs are going to be. So the output is just the solution, which is given by U here. So essentially, you can think of the PDE as a system that takes an input, in this particular case, the coefficient and the source, but let's say just the coefficient, and it churns out an output, which in this particular case is the solution of the PDE. In other words, it takes a coefficient, A here, as you can see, it has some spatial fluctuations, and then it churns out an output, which is given by the solution of the PDE. As you can see, the A does not look remotely like the input here, the coefficient does not look remotely like the output, because what the output tells you is how the fluid is distributed somehow. The pressure of the fluid is going to be distributed, right? So in other words, in this particular case, you can sort of say that solving a PDE is tantamount to finding out what is called the solution operator. Now, the solution operator is this object which exactly does the systemic transformation. It takes input and it produces an output. So it takes the input A, the coefficient here, and it produces an output, which is a solution to the PDE, which is given by this. Okay, so remember that this is the way you can think of differential equations, that these are transformations that take inputs to outputs, except that there is something special about these inputs and outputs. Unlike a standard function, which takes a finite dimensional input and provides a finite dimensional output, here the inputs and outputs, and these are functions, and these sorry, I don't know, some reason it, there you go. Anyway, so these inputs and outputs, both of them, the solution itself clearly is a function. So what do I mean by it? So the input itself is an infinite dimensional quantity because it's a function. It cannot be described in principle by finitely many parameters, and so is the output, a function which is described in terms of finitely many parameters. That's why the transformation that takes the input and churns out the output is an operator, because operators are generalizations of functions which takes infinite dimensional inputs and churn out infinite dimensional outputs. So this is a very important point here, that solving a PDE essentially is finding or computing or calculating or approximating the solution operator. And this is intrinsically an object that transforms infinite dimensional quantities into infinite dimensional quantities. And you'll see why this is an issue in a very short time. So this is one example, right? But is this general enough? An answer is yes, indeed. If you take another PDE, for instance, it's a time-dependent one. I just took one for definiteness, but there's nothing special about it. So these are the compressible Euler equations of fluid dynamics. For instance, aerodynamics, the flow of air just outside this room is going to be governed by the compressible Euler equations. And as you can see, these are much more complex PDEs than this simple scalar PDE, right? But if you're interested, these quantities have some meaning. Rho here is the density of the fluid. V is the velocity field. So in 2D or 3D, it's 2 or 3 components. E is the total energy. P is the pressure. And then you have an equation of state. There is an equation of state which relates them. And usually for an ideal gas, the total energy is given by P over gamma minus 1 plus half rho P squared, something like this. Okay. So this is a detail, that this is a fairly complex PDE. Now here, let's say that we fixed there are no sources, there is no forcing, there's no coefficient. Let's say it's a flow of air, so there's nothing to impede the flow. And then we have just a square domain, periodic boundary conditions, just for simplicity. All these can be additional inputs, and all that we are left with are the initial conditions. So here's an example of an initial condition, a typical initial condition that, for instance, happens when you look at the clouds. It's shear, so you have the density, and I don't know whether you can see this, but this is a shear. So the velocity goes in this direction, and here it goes in this direction. Okay, so there's a shear, and because of that, the flow becomes very, very complicated. And at a later time, as you can see, this is a very complex flow. So this is the density. What I'm showing here is the density. This is the density. But of course, every variable changes, and you can see that there are lots of complex vortices and fingers and so on and so forth. So fairly complex solution. But again, the idea is, so this is a solution at a later time, t. Let's say this is t equal to 1, some unit time in some idealized units that we have. So what is the solution operator in this particular case? What is the transformation that we're interested in? The transformation now takes the initial condition, and it produces a solution at a later time or at any given time, right? This is a trajectory. Any given time could be encapsulated in these terms, but let's say it's simply the solution at a later time. So again, it takes the A here is the initial condition, and U here is the solution at a final time, which is given in terms of the operator of the PDE. So again, it takes a function, clearly a function, it's defined at every single point. Similarly, the output is also going to be a function, right? So in other words, you have an operator which takes A to U dot T. The dot here means that it's sort of given at any given point in space. So again, it's the same story, that solving the PDE is the same as computing this transformation that takes an infinite dimensional function input and transforms it into a function output. Okay, so this is what it means, and we can sort of make it abstract so that things are easier to understand in some sense. I don't have to keep on writing specific PDEs all the time by simply taking an abstract perspective. So now remember that at the end of the day, we have functions which get mapped onto functions, and this is done by operators. So any questions about that? So this is the key setup that we are in, and we will deal with this setup. Okay. So now, just for simplicity, we take a function because our inputs and outputs are functions. So what we do is that we take a function space here, we take a function space here, and of course, since we are going to take data, we need some data distribution. So this mu, you can think of it as a data distribution. But the data is function valued now. Each time you're going to pluck a point, a sample of the data, you'll get an object like this. So just think you have a library of images, a library of functions, and you choose some at random. So that is the thinking of a data distribution. Okay, and then there is some abstract PDE. So the abstract PDE is clearly given here, the same as what we dealt with pins, no change there. And now the important thing is now I put both the coefficients as well as the sources in one bracket and simply say that there's a solution operator that maps x to y. So this here is G, right? So this is the abstract setup that we are going to do. And the task here is also very clear, because now for every PDE, we have associated with the PDE a solution operator, right? For instance, which takes the coefficients to the solution, or it takes the initial conditions to the solution, and so on and so forth. And now what we'll be given is data, right? So this data that is going to come to us, that's why I mentioned that there is a measure with respect to it. So what do? Let me choose this. So you choose AI from this distribution mu. So remember that AIs are functions, mu is a distribution on functions, so you have to choose this. And then the data that is given to you is AI and G of AI, for simplicity, plus some noise, okay? So this is going to be your data. So given this data, so A could be a large number, it could be a small number, it depends on the data set that you have. So for instance, if you think of weather and climate data, this number A is typically something like 60,000 members, okay? It will have 60,000 members in the standard weather data sets. But for some other applications, this could only be 5 members. So there is a huge disparity in the size of this data set. But it is not in the order of the sort of internet scale data that we have for text and images, where there are billions and billions of data points in some sense. So that this is going to be a challenge, right? So given this data, the task is to learn the operator, right? So learn G. So this is what is called operator learning. And as I said, means there is no other solution to this, because intrinsically your inputs and outputs are infinite dimensional. So you have to, in order to solve the PDE, you have to learn the operator. Are there any questions on this? Because this is a very, very important point. No? Everyone understands this? Also on Zoom, are there any questions? You can always ask questions on the chat box in Zoom. Okay, yes, of course. Yeah. You didn't get this part? Okay, I can explain it to you. No problems. So shall I explain it with this example first? So, okay, let me take you a very simple example, right? So let's say that even simpler, so that hopefully this will be much clearer and to everyone else. Let me give you an example. And maybe I don't want to clutter my writing even more. Let me write it on some paper. Okay, let's take a very simple example. Let us say that my domain is 0, 1 cross 0 t. Okay, doesn't matter if it's 0, 1 cross 0 t, means let me erase this, because now I have to improvise a little. So let's say that it's R, the real line cross 0 t, just for simplicity. My PDE is the advection equation. Several of you have seen this, I'm sure. Okay, and this advection equation, and this is given by ut plus aux equal to 0. And I took the whole line because I didn't want to bother with boundary conditions. Okay, and now your a here is, so, and your initial conditions are u naught of x. Okay, so these are functions, right? U naught of x is a function. So now your solution operator s of t takes u naught to st of u naught. And who can tell me what is the solution of this PDE? So given u naught, what is u of xt? This is just advection, yes? X minus 80, perfect. So this is just advection, right? So this is the solution of the PDE. So now, as you can see, that you start with any function, right? So let's start with a function. Let's say that is sine, some form of sine. After a while, what happens is that you get this, you get this transported. So it becomes something like this. Things move, right? So this is, so now what is the input here? This is a function. Sine of x is a function. And the output, for instance, sine of x minus 80 is a function. Now, you tell me, can you describe this function by a finite dimension? In general, you can approximate it very well with finite dimensional objects, but can you describe them entirely by finite dimensional objects? No, right? Because it's a function. So that's why it's an infinite dimensional quantity. You cannot describe it in terms of just one or a vector of finite dimensional quantities. And the output is also going to be infinite dimensional because again, it's a function. Okay, that's why it's a mapping between functions and functions. We don't need to think in terms of images. We can just think in terms of analytical expressions. That it takes sine of x, it goes to sine of x minus 80. It can take, I don't know, exponential of minus x, and it goes to exponential of x minus 80. So it's a mapping which takes any function and it maps to any other function or a relevant function, okay? You can take another mapping 1 minus x squared, and then it goes to 1 minus x minus 80 squared, something like this. You see? So it takes functions and it churns out functions. Is that clear to you now? Yeah. Oh, good. So you can always ask questions because then other people who are afraid of asking or don't want to ask, they also benefit from that. Good. So now let's go back to my slide here. So because we don't have to go fast, it's more important that you learn the concepts. So it's good that you ask questions. So this, as I said, is the core of operator learning, that you really have to learn. And this is, you'll see that it's not a huge difference, but a priori, it's a big difference from sort of what you have seen so far, right? Because what you've seen so far, let's say that you want to classify an image. An image is always given, at least in terms of what we have in terms of stock images. Let's say the MNIST, this is a standard image classification data set. These are 32 by 32 images. Okay, they're all 28 by 28 even, I keep on forgetting. 28 by 28 images. So the entire image is described in terms of 784 pixels, and that's it. But here, as I told you, also with this example, I don't have that kind of a description. So for a traditional sort of a CNN, let's say, or any machine learning task, so what you have is a 28 by 28 image, and the output is going to be some classes, right? So there are 10 classes, and you churn out the class probabilities. So you have a 784 dimensional input, and you have a 10 dimensional output. So it's a mapping between, let's say, vectors and vectors. Maybe of very high dimensions, but vectors and vectors. Here, in just conceptually, this is the difference, because now I cannot describe it. I can approximate it, and we have to, but I cannot describe it in terms of just 1 or 10 or 100 numbers, right? Because these are functions, this is a function, this is a function, this is a function. So intrinsically or implicitly, I have to work with infinite dimensional inputs and infinite dimensional outputs. And this is a stark departure from what you have seen before, where the DNNs, the deep neural networks, these were mappings from finite dimensional inputs to finite dimensional outputs. So there is an issue here, there's a gulf here. And for the next several lectures, we will see how we bridge this gulf, right? So is that clear? So the difference in paradigm, the difference in setup is quite stark. Okay, but how do we have to deal with this somehow, right? Means after all, we do make use of these frameworks. So what do we do? So first option that I give you is we cheat, okay? So actually this is, we cheat. Don't get confused, but there is at least many applications you can actually cheat your way. You don't have to solve this problem. But eventually in the next lecture, you will see that we have to get out of this cheating. We can't use this trick all the time, and we have to essentially solve the problems. So the point is, and maybe I could have even given you an introduction right here. So what if my input was, let's say, in this particular example, the cheating is can be made rather explicit, that my input distribution, so remember that my input functions U0 were drawn from a distribution mu, right? What if I said that instead of looking at all possible functions, which is unnecessary in practice, my inputs were given like this. So they were, let's say, summation of AK sine K pi x, okay? Summation of AK sine K pi x, and AK was uniformly distributed in -1, 1. Okay, and K went from 1 to 10. Okay, so in other words, so this was my data set, or the task itself is not to look at arbitrary functions, because that is going to, I'll give you some concrete examples. It doesn't make any sense in general, but it is restricted to a certain class of functions. That my class of functions is always given by these class of functions. So in other words, my input is given by these set of parameters. So these are my parameters. And what I can do is I can work with these parameters. So instead of an operator learning problem, I have a finite dimensional problem, right? Because now my inputs, just by definition, are restricted to this class AK. Remember, because these are the coefficients of a certain basis, and the basis is fixed. So now my input is going to be finite dimensional, right? And my output is potentially also finite dimensional. I can do that by simply taking AK, X, and T, and churning out my solution, which is going to be U of X, A, T, AK. In other words, I can rewrite my solution in terms of space, time, and some finite dimensional inputs. So this was 10 dimensions. This is 1 dimension, 12 dimensions, and a map to just one number. So this is 1 dimension. So in other words, by restricting the space of my data set, by restricting my task's generality, of course, you will see that you pay a price, right? But let's do this cheating for the time being. What I have done is that instead of having an infinite dimensions to infinite dimensions mapping, I have managed to escape by just having something which goes from 12 dimensions to 1 dimension. And this is what is called parametric PDEs. So remember that this was my setup. This is the setup in which I work. But the simplified setting that I told you is that the data that I'm going to draw, that's why I had this probability measure here. This measure has a finite dimensional support. Or it can be described, all the data, essentially this is a mathematical way of saying a precise, yes, James.
So if we put ourselves to a certain resolution, is that doing the same thing?
You will see that. Okay, there is a connection here, but at the moment I'm not fixing resolutions, right? I'm simply saying that my data itself is not coming from a very arbitrary class of functions, but it's only coming from a class of functions that are given in terms of finitely many parameters. So the number of degrees of freedom for my input is finite. And subsequently, I can also make the number of degrees of freedom for my output finite. That's why I said I'm cheating here, right? Because I'm sort of reducing, because all science in some sense is a reduction, right? You reduce what is unknown to what is known. We know how to deal with finite dimensional inputs and outputs. So somehow you have to project infinite dimensional inputs and outputs into this finite dimensional setting, right? And I'll give you a concrete example where this makes sense. So here, so this is what is called a parameterized PDE because, so for instance, in this particular example, now I'm running out of space here, I guess. But what you could have done is you could have looked at that this would be UT plus, okay, let's say that instead of A, I would have had a C here probably because, and this U naught depended not just on X, but on some A. Okay, this is this summation of vector A. So this is this AK sine K pi X. So in that case, your initial data, this is a parametric PDE because it depends, the solution itself depends on time, on space, and on the parameter A. Right? This is the basic idea. And here is an example which is much more, so I call the parameter Y. Sorry for the confusion in notation. So it's called the parameter Y. And this is finite dimension. It belongs to dy, but dy can be large. The dimension of dy can be large. So here is a concrete example for this, just to illustrate this point. So if you want to design a new aircraft, the critical design element is what is called designing the wing, right? Because aircraft is flown by the lift that is generated by having an aerodynamic wing that generates a lot of lift and that doesn't have a lot of drag. So this is the basic. So you cannot have a car which is going to fly, but a plane flies because it has this aerodynamic shape, among other things, right? So then, so if you design the wing, so what people do is, in general, to do anything in 3D is hard. So people take cross sections of the wing, because if you have seen when you've flown, you have seen an aircraft and you see that you can essentially compose it of cross sections. There's not a lot of variation within the shape of the cross section, only the sort of the dimensions, the length of the cross section. So along each cross section, you get what is called an airfoil. Okay, so this object here is an airfoil. Why is this not working now? Okay, airfoil. So this is like, think of it as a 2D wing, right? But it's, of course, when you put it together, you get a proper wing. So now in general, these things have to be manufactured, these things have to be described. And so what people do is that they have a certain base reference airfoil. So black here is a reference. Okay, so this is reference. And then they, of course, you start with a reference airfoil, which is based on the engineer's intuition, but you want to see whether you can increase the lift or reduce the drag or increase the lift to drag ratio and so on. So what they do is that they start with a reference airfoil, so some SREF, and then they generate some design space, okay? So this is some finitely many parameters, A from 1 to whatever, dy of y times, I have some concrete examples later, but perhaps it's easier to say that it's sy. So in other words, you can see here in this design, what is called the design envelope, that these shaded regions, this represent a whole set of shapes that are mapped by these parameters, okay? So these parameters, they are sometimes called as Hicks NA parameters in aerodynamics, but the details are not important. There are something between 20 and 50 parameters. So the entire airfoil, the design is somehow restricted, the number of degrees of freedom are restricted to these 50 parameters, up to 50. Usually people use 20. And then what you do is that you compute the whole flow field here. So here, as you can see, the inputs are, of course, the space coordinates, because this is steady state aerodynamics. You don't care what happens during takeoff and landing in terms of fuel efficiency, but you care about what happens during cruise conditions. So it's x, y, x, and this is the y is the shape parameters. So this is a concrete example of what I just illustrated the last time around, right? And then the output is simply the flow parameters, the velocities, the density, and so on. So these are functions, for instance, rho of x, y, and let's say the pressure, P of x, y, and so on. And from these parameters, you can compute things like drag and lift and so on. Body forces, which are just observables, okay? So the solution itself is in the form of a field, and otherwise drag, lift, these are sort of observables. So what we do by this cheating is essentially take an infinite dimensional problem, reduce it to finite dimensions, simply by restricting the input space and the output space. So we will, in some form or the other, we have to do it in general, but this is a sort of brutal way of doing it, right? You simply say that you look at finitely many parameters. But many people think of design, engineering design, as operating within this space, that you have finitely many parameters and you're trying to find optimal values within those parameters. Okay, how else can we design? Now let's assume that this is our problem, that we have cheated, we have projected our problem down from infinite dimensions to finite dimensions simply by reducing the measure, by reducing the data set that, the diversity of the data set, that the dimension of the data set that we have. Once we do that, it's just plain vanilla machine learning, right? These are the things that you're already familiar with, because now remember that my inputs are this X and Y, also T, if it's a time-dependent PDE. And then all that you do is I club it together, I call it as a Z. So this is T, X, Y. These are all the inputs. This is time, space, parameter. And my solution is given by some L of Z. This could be the field. It could be an observable, a quantity of interest. But it's a mapping between finite dimensions and finite dimensions. So you could just use your plain vanilla deep neural networks, means the usual things. You have these layers, you have the weights and biases. I don't have to tell you this. You have some activation function. And now, since we are not going to differentiate like we did with pins, we can take any activation function. It could be ReLU, for instance, which is the widely used activation function, right? And then how do we have data? The ansatz that we have, the sort of the argument or the hypothesis that we have for data usually is that this data is randomly generated, right? So this is the hypothesis. So what you can think of is that now these things, think of them as parameters in space. So for instance, within this set of shapes, you will randomly generate, let's say, 1,000 shapes. You'll compute the flow field with respect to 1,000 shapes. 1,000 is just a number that I gave you. That would be quite expensive because each of these computations will be between 1 and 2 minutes. Means even the fastest codes will be of the order of a minute. And when I was a PhD student or a master student like you guys, this was of the order of 2 hours maybe. So we have done like at least 2 orders of magnitude down. So things have improved, but it's still of the order of a minute. But if you generate 1,000, it's 1,000 minutes, which is some time, right? It's not serious time. So this is going to provide you with the data. So L of Zi is your data. You can think of this as your labels. So Zi's are the points at which the sampling is taking place. There could be some noise, but I'm operating in a noise-free regime just for simplicity. And then you look at the output of the neural network, which is given here. These are the predictions. And this is not, this is a regression problem, essentially. It's not a classification problem. So what you do in this particular case is that you just use whatever SGT, Adam, whatever, to minimize this loss function. So the algorithm itself is super simple. You have finitely many parameters. You take a random set of these parameters, generate some data, and then you learn the solution operator by using standard deep neural networks, plain vanilla deep neural networks. Any questions on this? No? From people on Zoom? No? Okay, so this is as easy as it gets. The question is this going to work out? What are the caveats? Do we have some issues? Let's see what happens. Right? So the first question always, at least for a mathematician, is that is this ever going to work? So in particular, if you're given some tolerance here, so this is some tolerance. The question is, can we find a deep neural network? Can we find a suitable architecture and so on, such that for the underlying map, you can think of it as an operator now, but it's really a map because operator has been reduced to a function. Can you find deep neural networks such that these things are close to each other? And if you remember the last lecture, I'd already talked about it, that we have this universal approximation property. And what does the universal approximation property do? It provides you the guarantee that, yes, there will always be even a shallow neural network, even a one-layer neural network, such that this is true. As long as this map is continuous, and in fact, even less than continuous, it could be integrable. It's as long as it's measurable, then indeed this can be done. Okay, so in principle, this is not a hard problem because it's finite dimensional, so you can always solve it. However, the point is, that there is a price that one has to pay with respect to complexity. So the size of this neural network, so let me say M is the number of parameters. Then there are some results which essentially say that the rate at which this convergence happens in general, of course, there are problems where it is, where this is the worst case guarantee, but in general, it scales with two things. It scales with the regularity of your map. So this S is the number of derivatives. So if you have a smooth function, S is large, right? It could be 10, 100, whatever. P is some integrability. Think of it as 1 and 2. And D bar here is the dimension. So D bar is the dimension. In other words, it's easier to learn smooth maps than things which are complicated. And it's easier to learn in low dimensions than in high dimensions. This is sort of the thinking that happens. And the point is that in general, this is not good because then you are hit with the curse of dimensionality, that even in sort of low dimensions, you will end up with very, very large network sizes. So if you do the math, then already you get into 100, no, is it 100 billion or no, a trillion, right? 10 to the 12 is a trillion. And this is even ChatGPT, the underlying model is not like that. So this does not explain anything, right? Because even with very, very low dimensions, you end up with very, very large numbers. So there is a curse of dimensionality, which I had already spoken about in the last lecture. But it turns out that that is not the case because at the end of the day, we are not looking at some random mappings here, right? These mappings are these functions, this L here, this object, these operators, if you want to think of it like that, these are much more structure in them. And the structure comes from the fact that these are solutions of PDEs. So solutions of PDEs could be smooth. They have other forms of regularity, dimensionality reduction. And essentially, there are lots and lots of results. There's some detail here. It's not important, but there are lots and lots of results which essentially tell you that this error, the earlier error, which scaled like exponential in dimension, it scales much better than that because of the solutions of PDEs. So this is for all kinds of PDEs, elliptic, hyperbolic, parabolic, and so on. There are lots of results. And this sigma here, which tells you the rate, this can be linear, quadratic, even logarithmic for some PDEs, okay? So if something scales linearly in dimension, it's not a big deal, or quadratically in dimension, it's not such a big deal. So there is some regularity or compressibility of the data, which tells us that at least in terms of the approximation error, the error that we get from in principle error of approximating this, we can do rather well, right? So this is not such an issue. However, the main point is that you also have other sources of error. I think Ben mentioned them at the beginning of his lectures. You have optimization error. This is our familiar friend, training error, that we saw a lot in the last couple of lectures. And there is some generalization error. And this is the one that I'm going to target here. Because once you have random points, remember that my data was supposed to be random. Once you have random points, then there is a limit to this. And the limit is given by, also we saw in the last lecture, there's essentially square root of n. Okay, morally square root of n, even though there is a logarithmic correction here. It's this always there because things are correlated. So essentially, at the end of the day, we can say that my overall error, this behaves in the following manner. And this is important, these considerations are important because it depends on the network somehow. But let's say this C is sometimes called in theoretical machine learning as a compressibility factor. Compressibility factor. Some people also call it as kappa, but I just called it as C. Okay, but essentially in terms of sample complexity, because this is for us an issue, this is always going like a square root. It's slightly worse than a square root. Even in the guarantee is slightly worse than a square root, but it is, let's say, a square root. And this is again a problem for us because remember that even if this was order of 1, let's say it's a number 1, and I want an error of 1%. So 1% is 1 over 100, right? Assuming that everything is of the order of 1. So if I need 1 over 100, so I have to find the number of samples. The square root is 100, and that is 10,000. So 10,000 is a lot of samples because just imagine, as I said, a single simulation takes me approximately 2 minutes. 10,000 samples will take me 20,000 minutes, and this is too much, right? In 2D, so in 3D, you can imagine nothing runs in 1 minute. In 3D, a single output of the code takes you anything from 1 hour on a small machine to hundreds or thousands of hours or millions of hours on a supercomputer. So one has to be careful. And this is some sense the big challenge that I'm trying to sort of pose here, that we are dealing with an object. So this is not like taking an image. Taking an image is cheap, compared to solving a PDE or solving differential equations or just simulating physics. So forget about the low regularity here. This is neither here nor there. But essentially, we are in a relatively, and this is relative, because also if you're looking at number of sick people, like in medical AI, that's even less, so it's one has to be relatively data poor regime. And this can be, to some extent, at least posed in contrast to the big data success of machine learning that has come up from large data sets, right? And towards the end of our course, I'll convince you that actually here also we need large data sets. But for the timing, let's pretend that we can never get access to large data sets. And we have to work with relatively small data sets, perhaps the order of hundreds of samples, not tens of thousands of samples, right? And how are we going to leverage that? And how are we going to use that? So there's no point in me starting a new topic. We will do that in the next lecture. Okay, so there's only 3 minutes left. Okay, so have a nice weekend. And next week, remember that Friday is Easter, Good Friday. So there's a holiday. We have only one lecture, and there we will talk more about operator learning and see whether this cheating works. So even cheating doesn't work here because we don't have enough data, right? So, and then what happens when you don't cheat? Okay, next week then. So long.